Today's a big day. We get to learn about projectiles. Projectiles are an example of two-dimensional motion, which means we have motion in both the x direction and the y direction. Now, there's only one force that's going to work on our projectile, and that's gravity. That's what causes our projectile to bend down back towards the Earth rather than fly off into space. So gravity is always acting down. I know it seems obvious, but you'd be surprised how easy it is to forget that. So it's always acting down, which means it only affects the y direction velocity. As you can see in this picture, as the projectile goes up, the y direction velocity gets smaller and smaller until it reaches its peak, and then it starts speeding up again on the way down. But the x direction has a constant velocity. There is no force in the x direction, since we're ignoring air resistance. There's no force in the x direction, so the x direction velocity is going to be constant. So let's look at how to solve one of these problems. So the steps to solve the problem. The first thing you want to do is you want to separate everything into an x column and a y column. We want to keep these separate because only time can pass between the two columns. Everything else has to stay in its own column. Now there is a variable that we know that we're usually not told, and that's the acceleration. Because we're talking about the acceleration due to gravity, we know that that acceleration is always negative 9.8 meters per second squared. And that's only in the y direction. There is no acceleration in the x direction. Now you have to write all your givens in the correct columns. So separate your initial velocity, which is probably at an angle, so both x and y. You need to separate that into the x and y components so that you have the x initial velocity and the y initial velocity. And then you need to pick what equation you're going to use and write that down. In the y direction, we could use any of the amigos, any of the kinematic equations. But in the x direction, we only use v equals delta s over t. Because there's no acceleration, we're not going to be able to use any of the amigos. And the last step is just to solve. Let's see how this goes. So here we have a projectile fired with an initial velocity of 40 meters per second at a 30-degree upward angle. And we want to find out how far does it go. So first, pick out your givens. We have the initial velocity and the initial direction. So we're going to separate things into x and y columns. So in the x column, we write our givens. And our given in the x column, the only one we have right now, is the x component of the initial velocity. We find that using v naught cosine theta, and you can figure that out until we get a number for our initial velocity in the x direction. Now let's look in the y direction. We have a few more things here. We can figure out the initial velocity in the y direction. We know that it starts and ends at the same height because it started and ended on level ground, so our change in our y displacement is 0. And since it starts and ends on the same height, we can also say that the initial velocity and the final velocity are the same, just opposites. So here we say that v final y is negative v initial y. That's only true if it starts and ends on the same level. We don't know time, but we do know the acceleration because it's taking place on Earth, so our acceleration due to gravity is negative 9.8 meters per second squared. So let's look at what equations we're going to choose. Now in the x direction it's easy. It's always v equals delta s over t. Since we're talking about the x direction, we can call it delta x over t. The y direction, we have a few to choose from. So if we look at our givens, we see that we have plenty of things. We could actually choose several equations, but let's go with this one, delta y equation. We can see it has everything in there except v final, so we didn't actually have to find v final first, which is good. Some problems it's hard to find v final first. So here's our equations. Let's see what we're going to do with them. So in the y direction, we're going to be looking for time because we ultimately want to find the distance that we travel in the x direction. So in order to do that, we need to know how long we're in the air. So let's use the y direction to find time. So let's rearrange our equation for time, plug in our numbers, and then we get that we're in the air for 2.02 seconds. Now it doesn't matter if you're looking in the x direction or the y direction, you're in the air the same amount of time. That's why time can go back and forth between the columns. So we take our time here, and then we're going to use it over in the x direction. So in the x direction, we take our equation. Let's rearrange it for delta x because that's what we're looking for. Plug in our numbers, including our time that we just found, and we get our answer, 40.4 meters. So let me give you some tips for solving some of these projectile problems. Horizontal projectiles always have a theta of 0. Now you could also say that the initial y velocity for horizontal projectiles is 0, and the initial x velocity is all of the velocity. Or you could just say that the horizontal projectiles have a theta of 0 and figure the rest of it out. At the peak of a projectile's motion, as it goes through the air, once it reaches its peak, and before it starts going back down, the y velocity is going to be 0, but just momentarily. Just like when you throw something straight up in the air, it pauses at the top momentarily and then starts coming back down. So we can use that if we want to figure something out about the peak of a projectile's motion. And like I said earlier, if it starts and ends at the same level, your v final y equals negative v initial y, your y displacement is 0, and the time at the peak is half of the total travel time. That could be useful if the situation calls for it. And in the x direction, since there is no acceleration in the x direction, we have constant velocity in the x direction. That means that your v initial x equals your v final x equals your vx anywhere. So we don't have to worry about finding initial x or final x. Once we know one of them, we know the other. And everybody's favorite example of projectiles, Angry Birds. Lots of time gets wasted there, but a lot of practice with projectiles. Yeah, we'll call it that. See you next time.